So I think we must start. So, okay, welcome to the last day of the online international workshop on advanced topics in dynamical systems. Again, thank you very much for your coming, for sharing your valuable time with us, and let me remind you about two initial things: that we are recording this meeting, so by participating you accept the record, and the second is that we are now the discussion will be at the end of the presentation, so please you can type your question or comments in the chat, or you can turn on your camera and raise your hand and ask your question. So today we have Professor Hayder Naji from University of Baghdad, and he will talk about chaotic dynamics in ecological and epidemiological models. So please, Professor.
Okay, welcome everybody. Today I might talk about chaotic dynamics in ecological and epidemiological models. As you know, this type of dynamic was very known in engineering systems like electrical engineering and others. And there is no evidence of existence of chaos in ecological system and epidemiological, in general in biological system. Although this type of system has all things what happen in nonlinearity and higher dimension, and also other types of ingredient for existence of chaos. There is no evidence up to 1991, and after that start with Hastings and Powell in his study of chaos and in a three-species ecological system. That's what we give after give some information about objective and mathematical tools used in this type of study. Then we give some example. From that example, we will give Hastings and Powell example. Now, the objective of this talk about this lecture today, it is to give and better understand for order and chaos that will occur in three-dimension higher models. Why three-dimension? We will explain why three-dimension. Because in dynamical system, autonomous type, there is no any type of chaotic or quasi-periodic in two-dimension orders. It is start from the three-dimension and above, and that given by Poincaré induction theorem. There is a lot of mathematical tools used for detecting of chaotic dynamic, like Bifurcation Diagram, Attractor dimension, from which Lyapunov dimension, one of these Attractor dimension, Poincaré section, strange Attractor. We will use today three of these, which is Bifurcation Diagram and Lyapunov Exponent and strange Attractor, and this will be given details after this slide. In general, some basic concept we have in chaos theory is a branch of mathematical focusing on the study of chaos states in dynamical system. What's meaning by chaos? In general, it is disorder, and this type of attractors or this type of study has one property. It is highly sensitive to initial condition. That means we maybe start very near to each other, 2 points, but the solution will be diverge from each other with time. This is the sensitivity of initial condition, and there is some properties will be used to compute this degree of the sensitivity of initial condition. One of these is the Lyapunov exponent. There is no mathematical definition for the chaos up to Robert Divani definition. It is in general say a dynamical system is chaotic if it have these properties. There is three properties for dynamical system. If it is happen, then we can say this dynamical system is chaotic. The sensitive to initial condition, topologically transitive, and it should have dense or periodic orbit. The 2 points, last 2 points, topologically transitive and dense periodic orbit, these two is existence actually in the first one, sensitive to initial condition. For that, we will see, we will focus on the sensitive to initial condition. If this happen in any dynamical system, then it is directly has the topologically transitive, also have dense of periodic orbit. For that, we will go further to give some information about the tools like bifurcation and the Lyapunov exponent. So we can go further to example. We have to understand what's meaning by bifurcation, or especially bifurcation diagram, and what we mean by Lyapunov exponents. The term bifurcation refers to significant change in the dynamic of fixed point or periodic point or other set of dynamical interest of summarize the qualitative. This is what mean by bifurcation. It's mean qualitative change in the dynamic, not quantitative change. Means we have different, maybe increasing in fixed point or decreasing, and maybe the stability type of that point will be different, completely different. We use bifurcation diagram for detecting chaos. What meaning by bifurcation diagram? We will see some example given the bifurcation diagram. It's simply in a plane. We have it run in a plane. On the x-axis the parameter, and on the y-axis we will put the maximum of one variable of the system. Then at that time we will see what we have from that bifurcation diagram. It is give the birth, evolution, and death of the attractor set. So the bifurcation diagram gives the lifestyle of the trajectory of the solution. From that bifurcation diagram, we can say this area or this point is chaotic, or this point is periodic, or this point is a stable point. Also, Lyapunov exponent, the other tools of detecting chaos, provide a way to identify the average rate or divergence, whether it is increasing or decreasing between the initial nearby orbit. They are similar to eigenvalues used in the local stability analysis. In fact, it is generalization for the eigenvalues. That means eigenvalues detect or gives the degree of the moving in the x-axis or in the y-axis or in the z-axis at the point, while the Lyapunov exponent gives that degree on the entire solution, on the entire trajectory of the solution. So Lyapunov exponent describe what happened near an entire trajectory rather than describing what happens near a fixed point. It is well known for the n-dimensional system. We have n Lyapunov exponent. That means if we have dynamical system of dimension 3, we have 3 Lyapunov exponent. If it is of dimension 4, we have 4 Lyapunov exponent. So the number of Lyapunov exponent is dependent or equal the dimension of that system. The mathematical formula for computing Lyapunov exponent in the map, one-dimensional map, is given here. This is for computing Lyapunov in one-dimension map. But we have talked about higher dimension. So in this case, we have number of Lyapunov exponent. For any attractor, we should have the summation of these Lyapunov exponents should be negative. The sum of the Lyapunov should be, because we have attractor. That means we have the asymptotic behavior to that attractor. So we should have the summation is negative, but this is, we talk about the hyperbolic system. like we explain here. See, we say here we have for the hyperbolic attractor, we can classify this attractor as follows. For a stable equilibrium point, we should have, if we arrange it from the descending order, we should have the first one is negative and for all I. But for a stable limit cycle, we have 1, 0, and the other is negative. For a stable torus or a quasi-periodic, we have 2 of Lyapunov exponent equal to 0, and the other is negative. We see from this, all of these satisfy the condition above, the summation is negative. This is for the attractor of the 3 type, which is hyperbolic attractor. We mean when we have a stable point or stable limit cycle or a stable quasi-periodic. On the strange attractor, the case is different. In the strange attractor, we should have one of these Lyapunov exponent positive. At least one is positive. Now there's other type of studies about the hyper chaotic. It is talk about number of these Lyapunov exponent is positive. That means maybe the sum is not negative. In chaos case, in chaotic, simple chaotic, we have at least one is positive, especially when the dynamical system is bounded. We should have that sum is negative, but still in chaos case we have at least one of these Lyapunov exponent should be positive. This simple example, it is very known example about logistic map. It is map. Now we don't talk about the continuous case. This is in discrete case, and I will explain in the next slide why I talk about discrete and continuous, because there is difference in occurrence of chaos. In discrete case, it may be appear even in one dimension, like logistic map. We can see from logistic map, this is the map of logistic, and this is the bifurcation diagram for logistic map. Here we have different type. In the beginning, we have stable point. Between 3 and 3.4, we have periodic, and then period 4 and period 8, and then enter to chaotic area. This chaotic area, if you draw a vertical straight line like this, from the above to low, we can see we cut in the interval of point. We get set of point. Whatever in the beginning we have only 1 point, and only 1 point means a stable point. Here 2 point we have periodic, and when we get number of point like interval, then we get chaos region. This is in one-dimensional map. When we have one-dimensional map, we see we get in discrete case we have chaos. That's not occurs in the continuous case. And I said here, on contrast, for the continuous dynamical system, Bunker-Ebdukson theorem is very known theorem in the dynamical system, shows that the strange attractor can only arise in 3 or more dimensional. Why Bunker-Ebdukson theorem said that? Because in Bunker-Ebdukson theorem, we specify the type of attractor in 2 dimensions. In the plane, Bunker-Ebdukson theorem said we either have fixed point or we have periodic point. We cannot have any other type of attractor in the 2-dimensional system. For that reason, when we talk about chaos, we have to talk in continuous case about 3 dimension and above. We cannot have this type of attractor in the 2-dimensional system. And that comes from the fact it is well known in dynamical system. It is Bunker-Ebdukson theorem, which is talk about the type of attractor in the plane, in 2-dimensional, either point or periodic. This is very known example in the engineering systems, not in ecological or epidemiological. You can see the Lorentz system. This Lorentz system contains 7 terms. Lorentz system, 3 equations, and the 7 terms. 5 of them is linear, and only 2 of them is nonlinear term. And the nonlinearity is very little here. And also, we got butterfly wings attractor, which is a very famous chaotic attractor. It is very known type of chaotic attractor. It is called butterfly wings. You can see at this point either go to the left or go to the right. We cannot have any sensitive, we don't have any order case here. That means the sensitivity is very high in this type of attractor. When we start at any 2 points near to each other, maybe the first one goes to the left and the second one goes to the right. So the system is highly sensitive to initial condition and it is well-known chaotic system. Now we transfer to the our object in the ecology or epidemiology. We start with very famous model. It is a 3-species food chain, and this is given by Hastings and Powell in 1991. And this is the first attempt to detect chaos in ecology, or in general in biological model. This was the first attempt to study this type of attractor. He gives example of food chain. This X variable represents the prey, and Y represents the intermediate predator, which is preys upon X, and Z it is top predator, which is preys about Y. So for that reason, because each variable has a connection with the next and with the above only, it is called chain. In food web, we have maybe multiple connection before that level or after that level. Like, but in here in the chain, we have this type of connection. This food chain, we have F here called the function response, and that response represents the attack rate of any species, predator species, for that prey. This type of attractor is now prey dependent and given by Holling and in 1959, I suppose. This type is called Holling type 2 function response. And for this simple food chain, and with using this parameter, we got chaotic attractor. You can see this attractor, it is called inverted teacup attractor. It is simply look like teacup, and this is a chaotic attractor. And this is the time series. We can see from the time series, it is clear, it is not straight line like simple case in stable case, and it is not like sine or cosine moving very similar to each other. So it is not periodic. But in chaotic attractor, the time series, the trajectory of X against the time, it is simply not, there is no similarity in each point of that time. So this is also for Y and this is for Z. So from these type of trajectories, we got this is attractor, and it is very known and chaotic attractor. He also, in his paper, see or check the sensitivity. He started from 2 points different by each other about 0.01, only 0.01. But you can see with time, it is start the moving diverge from each other. So for that mean, this solution is sensitive to initial condition. Also, he draw the bifurcation diagram in this one. He choose one parameter of this system. It is B1, and draw it against the maximum of Z, which is the top predator, maximum of Z, and he got this type of attractor. You can see here we have a stable point, here we have periodic, and then after that we tend to periodic, and so on. This region, there is a lot of chaotic region in between. This is the first example was. And after that, there is multiple studies for this type. I have one of these studies. I study this type of food chain. It is different about Hastings and Powell. This is order occurs in predator to prey ratio dependent food chain. And this, it is different about the first one. We have ratio dependent. We have predator to prey, and there is mathematical change here because It is not defined about 0 for U1 and U2. And although this system is also type of other type of food chain, we use this parameter, biologically visible parameter, and we take Y1 and W1, sorry, and W6 as in this range, with fixing W6 here at 0.04, and in the other case, we fixed W1 at 0.177, and we got this bifurcation diagram. This is for W1, and this is for W6. Also, I draw the Lyapunov exponent. You can see from here, this region in bifurcation diagram, it is very dark. That means it is chaotic. You can see directly after that, largest Lyapunov exponent, it is positive. It is above the 0, here 0. You can see there is also here positive region, here positive region. So whatever I have in bifurcation diagram for dark point, we have positive Lyapunov exponent. This is for W6 again. We have also positive Lyapunov exponent. This is type of diagram known as Lyapunov exponent bifurcation diagram. This is also means clearly what's happened for the chaotic region and stable region in between. And we draw the strange attractor for some point of W1 and W2. You can see the strange attractor. This is not periodic or a fixed point. So still the solution in this geometric object is chaotic system. This is other type of attractor. It is food web, not food chain. We can see here X and Y and Z. X is a prey, Y is a predator, and Z, it is generous predator. This Z, it is taken from both, from Z and from Y and from X. For that reason, it is web, it is not chain. Also, we can use here a different type of functional response. We used here the Holling type 2 and dangerous type of functional response. What's meaning by functional response? It is rate of attack rate of predator to prey, and you can see also from this attractor, from this system with this biological system parameters, we have here two bifurcation diagrams, and we draw some attractor in some range here in bifurcation diagram. For strange attractor for W2 3.17. Also, we draw it for W1 bifurcation diagram, and we can see this type of attractor. It is chosen for W1 equal 1.44, and you can see 1.44 here in this bifurcation diagram, the left. It is chaotic region, so we got strange attractor in this diagram. Other type also, this is, I think we finalized with some friend from India, Professor Ranjit and Dubey and Rao. We got from this type of food chain, it is different about the others by complexity of this form here for the Z. And we got for this biologically visible parameter, this type of strange attractor. It is look like a big hat. So this is the strange attractor. We got it for this type of system, and we draw here different type of bifurcation diagram, and also Lyapunov exponent bifurcation diagram. We can see from here we have positive region here in Lyapunov exponent. We have maximum Lyapunov exponent positive region here. We have positive region here for Lyapunov exponent, large Lyapunov exponent against W7. And in all these cases, we have chaotic region. Now we transfer to epidemiological model. In this system, I have disease in the prey. I have prey, which is divided in two compartments, susceptible and infected. And we have a predator, which is taken from both susceptible and infected. This system is an example of epidemiological models, and also we use this parameters set, and we draw the bifurcation diagram. You can see from the bifurcation diagram we have very dark area hairs, and in between there's windows of periodic, and we choose a point here for this dark area and draw the attractor. It is look like butterfly wings strange attractor. This is the strange attractor what we get here. So it is a butterfly strange attractor, and this is the time series and sensitivity of this strange attractor. This is different type of bifurcation diagram for the same system, and from this bifurcation diagram for C as a parameter, for E1, E2, E3, all these parameters, I draw the bifurcation diagram and see the dark area, which is means the chaotic happen here and here and here. So many chaotic system. It is very sensitive system for the moving a parameter. So you can see some example of strange attractor. This is a butterfly wings of strange attractor. This is here also, and this is periodic. You can see the difference between chaotic and periodic. This is long periodic, and this is period 6, and this is period 1. You can see period 1, only one cycle. This is 6 cycles, and this is more, and this is chaotic. What we get from this, we move to the chaotic through a cascade of periodic doubling leading to chaos. This is the idea here. To reach the chaotic, we have to move through a sequence of periods. Today I found this paper actually. This is published just now in 2020. This is for some researcher, I think, and Andreas and a friend. It is talk about chaos and disease outbreak among prey. That means he has a prey and a predator, and there is some disease in a prey. You can see this is infected prey, and this is susceptible prey, and this is immune prey. This type of prey get immunization for the disease, and they formulate the mathematical model or the system, real life or biological system in this food chain or this system of differential equation, and then they made dimensionless and got this system on the right hand, and they draw some attractor. It is very nice attractor, like this on the left. It is called quasi-periodic attractor, and this is a chaotic attractor. You can see the difference between chaotic attractor, between the chaotic attractor and quasi-periodic attractor, and the difference in some parameters from this case to this case. So they get for this type of system chaotic attractor available, also strange attractor in 3 or 4 dimensions. Thank you for your attention. Thank you, Mr. Ali.
So, okay, thank you very much. And actually, I will start the question. So, the systems are entitled as ecological and epidemiological, but can you please explain how they exactly applicable in that area? I mean, in biological or in ecological, so where we can use them?
We can use this system in biological system. We can you can describe any system, any real life system, as a food chain or food web, or always we have interaction between the species.
I think we lost the speaker. Professor Raed, I hope he will join soon. الدكتور صوتك ماكو دكتور. خليه بس أتأكد. والله صوتك ماكو. أيوه. Okay. So speaker is joining us again now. It's some technical problems, and okay. I hope the speaker will join us soon. So anyway, sorry for this. Unpredictable. So chaos or chaotic system are unpredictable system. So and we live in now in unpredictable situation according to coronavirus, and many things can happen. So can we so we can enjoy this unpredictability. I mean, by staying at home. Actually, staying home is it means enjoying the unpredictability. So I hope I see.
Not happening through the
Yes,
through the lecture.
We have your voice now.
Okay, okay. You got my answer about the question. There's many applications for the ecological system and epidemiological system in the life.
Of course, I believe there are a lot, but I wanted I actually at least want to understand what is going there.
This type of system was
Mr. Hakimi, can you please turn off your microphone? This is Hakimi.
Chaos. Now it is important to study this type, and you can detect about chaotic dynamic in this type of system.
So actually we have also in the chat a question from I hope I will announce the name in correct way, is Divo Postado. He asking, can you please mention using which software the bifurcation diagram are plotted? So I think MATLAB.
I solved the system using simply numerical method, predictor corrector method, using C++. Then I draw the figure by MATLAB. But the solution is used with my program simply by using MATLAB. Actually, there is a lot of question about this type of from entire world. They ask me about the program of bifurcation diagram. I depend when I formulate my program. I depend about the original copy of idea of bifurcation diagram, which was available in Wolf in 1985, I think. It was written algorithm in Fortran 77, describing the idea about bifurcation diagram. From that paper, I can or I succeed to written my program. So I depend about my program in C++. But when I try to draw the result of that program using MATLAB.
Okay, actually, I think Dr. Muhammad Sahabi also want to ask a question. So, if he is still here, so please, your question.
Okay. Assalamu alaikum.
Salam.
عليكم السلام ورحمة الله وبركاته.
Thank you, Dr. Raed, for your interesting presentation.
You're welcome.
Yeah, you introduced some application for dynamical system, especially for system of ODE, in 3 questions and 4 questions. We know the level of function constructed for this system, and also this system sensitive for initial condition. My question: we can extend it, or you can explain some application for partial differential equation, and we can construct level of function for this system of partial differential equation.
Actually, in my example, I give some example. It is only ordinary differential equation, but it is available. So many system about partial differential equation, especially for diffusion case. When we included diffusion factor in your system, at that time we got 2 independent variable. So in this case, we have to formulate our system using partial differential equation. And the rest of the study is the same. We can solve it numerically, and we discuss it simply as we know. There is no difference, only in the way of solving.
Okay, in this case, this system of partial differential equation has boundary or only initial?
No, it should have boundary also. Should have boundary.
Should have boundary.
It should have.
Okay, thank you very much.
Thank
Thank you
you.
for you.
There are any questions or comments? If there are.
Hello.
Hello.
Professor Ali, myself, Dr. Sadiq Ali from India.
You're welcome. Please, your question.
You're welcome.
Hello, speaker, and hello, everyone.
Hello.
Actually, I have 2 questions. One is, can we extend Hastings 3 species food chain system to fractional order form? And if it is possible,
Yes,
then how bifurcation analysis will help to analyze characterization of such systems with fractional orders?
I saw a lot of systems for this type of study. They use the fractional differential equation, but they not go further for the study as this type of study. They go to solve this and they study the stability. Till now, I don't enter to this area actually for
what do you think whether
you talk about chaotic.
Yes.
Yeah, till now I don't try for that area. I don't have idea till now about how we can formulate the program for this case. Till now I don't try.
Okay. Thank you, sir.
Maybe in the future we can work about.
Maybe. Okay. Just I want to know that whether the bifurcation analysis will helpful to analyze such systems or not.
It should. I'm sure it's help. I'm sure it's help. But I told you until now I don't tried. So maybe we can help each other in the future. No problem about that. We can work about that.
Okay. Thank you very much, sir.
Okay. Welcome.
Thank you. So there are any question? So I think there are no more. And I would like to ask the Dean of Faculty of Computer Science and Mathematics, Professor Al-Janabi, to close the workshop. Please, Professor.
Yes, Dr. Ali, can you hear me, please?
Yes, we hear you. We have your voice.
Thank you very much. مساء الخير, good evening and dober večer. I am talking to you on the behalf of our university president, Professor Yasser Al-Mansouri. He sends you all his best wishes. Let me say very few words to our great keynote speakers, to Professor Ilya Spitkovsky from New York University, Abu Dhabi, UAE, Professor Ali Rida Ashrafi from University of Kashan, Islamic Republic of Iran, and Professor Kamel Naji from University of Baghdad, Faculty of Science from Iraq. We at the Faculty of Computer Science and Mathematics are very grateful for taking time off from your busy schedules, really from your busy schedules, to attend this workshop as keynote speakers. Let us all go away from this online workshop with one mind that the best way to serve our communities and to combat the common problems is to work together and to share knowledge. Many thanks for all who made this workshop possible. Many thanks for the department chair, Professor Abdel Hamza, and the department staff, organizing committee and scientific committee participants, and many thanks and gratitude to the people behind the scheme. We are looking forward to see you next year in a new version of this workshop at the university campus in Iraq. Thank you very much, Dr. Ali.
Thank you very much. And let's thanks all the speakers now for 3 days, and thank you very much, Professor Spitkovsky, and also Professor Ali Ashrafi, Professor Raed Naji. Thank you very much. The presentations were grateful, and thank you for all participants for coming and make these meetings happen and enjoyable also. Thank you very much. See you again soon in reality. Thank you very much. If someone wants to say a word, please, you can turn on your microphone and say your words.
Okay, goodbye.
Thanks to you for your help, for your work on this workshop.
Thank you very much, Professor. Thank you very much. Thank you for your accepting the invitation and for your presentation for valuable time. Thank you.
Yes, and thank you, Ali. Thank you, everyone.
Thank you, Professor.
Good night now.
Good evening.
Thank you for your valuable time, Professor. Thank you very much for your coming and make this event happen. Thank you very much. الآن في نهاية ورشة اليوم يعني والآن so I will speak in Arabic little words. شكرا جزيلا لكل الحضور لمن شاركنا هذه الورشة. Professor Kaptanienko, thank you very much for your time and enjoying this and coming to this workshop, and actually I hope to see you as soon as possible in reality. Thank you very much. Professor Ahmedov, thank you very much for coming. Also we have Professor Ahmedi, thank you very much. And we have Professor Arthur Borisovich, thank you very much for your coming and sharing your valuable time. All participants, Dr. Muhammad Sahib and Sanzol sorry if I could not pronounce in a good way, and all participants from our faculty also thank you for your coming, and all of you thank you, and see you again soon. In Arabic they say inshallah, so it means
شكرا جزيلا
after
دكتور.
finishing this.
موفقين إن شاء الله.
Thank you Professor. Thank you. شكرا دكتور علاء. دكتور حسين مساعد علمي رئيس جامعة المثنى، شكرا جزيلا لحضورك.
شكرا شكرا
Hakim,
دكتور
thank
عفوا
you very
شكرا
much for your coming. I actually have Dr. Sadr, thank you for your coming. And all participants, thank you very much, and see you soon as possible as in reality. And actually, good night.